Hello, everyone. I'm Bharathi Seshadri. We are pleased to present our work on Crash Analyzer, a tool based on LLVM for analyzing code files. This is a joint work done by Djordje Todorovic, myself, Ananthakrishna Sowda, Nikola Tesic, and Ivan Baev. This is the outline for our talk today. We will begin with motivation for this work and describe our design goals and architecture. We'll go over the details of the various modules involved, and we will conclude with a demo and some directions for the future work. Let us look at the motivation. So typically when triaging software crashes, the developer uses live debugging methods using a debugger such as GDB or LLDB, and offline debugging by inspecting the functions in the backtrace, looking for unusual argument values or control flow. And test engineers also use some of this information to route the bug to the appropriate component owner for further triage and quick resolution of the bug. So our question is, can we get more insights into the root cause of the problem? And in this regard, we came across an interesting work, Retracer by Microsoft, a proprietary tool that greatly assists QA engineers to file bugs against the right code owners, and also assist developers in triaging software crashes by performing analysis using memory dumps. And we have attempted to implement this idea in the LLVM framework. So our main goal here is to assist with fault localization when a software crash is involved due to access violations. And we would like to identify the function that is responsible for setting up the invalid access. And we like to leverage the existing LLVM and LLDB libraries to build a framework for this crash analysis. So let us set our expectations right. So this approach is effective only if the origin of the problem and the fix lies within the scope of the same crashing thread. So if the problem originates in one thread but manifests itself in another thread, then it is not a candidate for this approach. We can identify if the faulty function does not lie with one of the functions in the backtrace, but it is called by one of them. However, we do not aim to address issues that occur due to memory corruption, memory allocation issues, race condition, timing issues, stack overflow, etc. There are often other tools and techniques that can be used to address some of these issues. So let us look at the various building blocks of the crash analyzer. The input to the system is the core file and the program binary. So first we have the Corefile Reader. It extracts all the functions, registers, memory state from the backtrace of the crashing thread, and it is a snapshot taken at the instance of the crash. Then we have the Decompiler that produces machine IR for all the functions in the backtrace, along with the register state and global state. It also provides the MIR for other functions that may need to be analyzed. And then we have the analyzer that performs both the forward and backward analysis at MIR level, and we'll see why. Finally, we produce a taint flow graph and a function that is likely to be responsible for the crash. So let's take a simple example. We have main that calls a function f, that calls function g, and that calls function h, and then the program crashes inside of h. So the output we aim to report is that the name of the function f that is likely to set up this invalid pointer that is causing the crash. So let us now look at the various modules involved, and Djordje will get started with the Corefile Reader.
Yeah, thank you, Bharathi. Hello, everyone, again. I'll be talking about key components of our project. As Bharathi has just shown, this is the first phase of our tool. First of all, I would like to mention that our tool was implemented as a set of libraries representing each of the key stages. Once again, for those who are not familiar with the core files, I just want to emphasize once again that it is a snapshot of the process from the moment of the crash. It contains all sorts of information such as register values, memory content, and so on. The library that is responsible for reading the core file was implemented as a wrapper around LLDB library, from which we are using the API for reading the registers and memory content, backtrace as well, and stuff like that. All of that will be used in the next phases, and I'll cover that in a moment. And during the implementation, we've been using well-known techniques from LLVM development, including the debug-only functionality used for debugging purposes, and it is implemented for each of the modules. So decompilation. Before we move to the decompilation process, I just want to quickly mention a classical compilation process from LLVM. Yeah, we usually start with a source code written in a high-level language, let's say in C. Then we have a LLVM IR. After that, we have LLVM machine IR, which is closer to the final machine. And at the end, we have a assembler printer. Decompilation process is reverse process of that. So we use LLVM machine IR for our analysis, and I will talk about that in a minute, about the motivation for that. Next slide, please. As a first step of the decompilation process, the tool performs disassembling part. The core file contains text segments for all the functions from the backtrace. So at the end of this step, we have assembly instructions for each of those functions. Next slide, please. So in order to use existing LLVM ecosystem, including all the program analysis and optimizations, we needed to pick either LLVM IR or LLVM machine IR code abstraction. Doing it on the pure assembly isn't very convenient by using LLVM. So therefore, we decided to use LLVM machine IR. Why? We were satisfied with such a code abstraction that is as close as possible to the final assembly, which implies that our decompilation process won't be too complex to implement. And it actually answers the question why we haven't picked the LLVM IR, even though the taint analysis would have been even simpler than existing one on the machine level. So how our decompiler actually works, it first translates the LLDB assembly instructions into LLVM's MSINs, and then from those, it creates corresponding machine IR instructions along with machine IR-based blocks, machine functions, including all the attributes and so on. So final outcome of this phase is machine IR module containing all those functions from backtrace. And for each machine IR function, we create a dummy IR function so we can attach corresponding DI subprogram metadata and other useful debugging information that are being used during analysis on the machine IR level. We also recreate contraflow graph. Also, a very interesting thing we are incorporating into machine IR are register values read from core file. We are using that information during analysis, but we'll talk about that later. Also, we perform our analysis in backward direction from the crashing point. So we read program counter at the moment of the crash, and for such machine IR instruction, we attach this special crash start attribute, so we know from which point our analysis should start. Here's an example of machine IR module. We generate, as we can see, all the information stored as LLVM optimizer. On the left side, you can see information about target. There is dummy IR part. as I said, mostly used to attach DI metadata used in the machine IR part when marking debug locations of machine IR instructions. And on the right side, we see machine IR function. Yeah, this is the attribute representing register values that are used during taint analysis. And attribute with a color with a yellow is a special attribute attached to that machine IR instruction, which indicates where our analysis should start from. Also, you can see that each instruction has debug location attachment. Also, I just want to mention someone may find machine IR like this useful for some other analysis as well. As I mentioned, we read debug info sections and map some of them into machine IR. We are using debug info attached to instructions when reporting blame function. During analysis, we identify instruction that is responsible for introducing the crash. Then we read scope information from debug info attachment by reporting the function from it as responsible one. By doing that, we can handle situations where a blame instruction comes from a region of the code that is being inlined. But we'll show an example of inline function during the demo. So Bharathi will continue with the analysis part.
So as we've seen before, the goal of the analysis is to try and identify the function that is responsible for setting up an invalid address that led to the crash. So the analysis is done at MIR in Y. The primary analysis is a backward taint analysis. And in order to perform this analysis effectively, we depend on other analysis such as concrete reverse execution and register equivalence. We will look into these shortly. Next slide. So we perform a backward analysis by doing post-order traversal of the control flow graph of the machine function from the instance of the crash, that is due to an access of invalid address, till we find the instruction that is responsible for setting that invalid value. The taint analysis typically involves 3 steps: identifying the value to taint, propagating the taint, and termination of the taint. So to start the taint in our case, we inspect the MIR that has this crash start attribute set up by the decompiler for the very top function of the batteries, and we taint the memory operands in this instruction. So we identify the symbolic address using the base and the index register. If we know the value of the base and the index register, then we calculate the concrete memory address of this operand and taint that as well. And then we propagate this taint by inspecting the destination and source operands for each MIR. And if we find the destination operand to be in the taint list, then we remove that from the destination operand from the taint list and replace it with the source operand. And when we enter a machine basic block for analysis, we before we start the analysis, we merge the taints coming from the different parts into that machine basic block. So for example, in the picture on the right, when entering machine basic block 5, the taint list T3 and T4 coming from the 2 parts are merged before analyzing instructions from machine basic block 5. And when we encounter a function call, currently we propagate the taint through that function if either of the 2 conditions are true. If the return register, say RX in the case of x86, if it's tainted, or if a global variable is in the taint list. So presently we do not have a way to identify if an input parameter that is tainted is modified within that called function. So we continue the taint analysis until the taint list is empty or we have exhausted all functions in the batteries. And when we see a store instruction that has its destination operand in the taint list and a constant value is written into it, then we mark that as the end of that tainted operand, and we record this instruction. So we mentioned that we taint concrete memory address, and there are certain challenges in propagating the taint of such values. So Djordje will explain how this is being handled.
In order to be able to calculate more of those concrete memory addresses, we've implemented some additional utility modules. First of them is concrete reverse execution. So what is the purpose of that? During the backward walk of our taint analysis from the crashing point, we try to keep register values valid for each program point by applying inverse function of each instruction to the register value content. Okay, so as we can see on this picture, if we faced an add instruction, we try to apply an inverse function to find f1 minus 1, which is subtraction for add, and we apply that on the corresponding input in the register value machine function attribute. So next slide, please. An ideal scenario would be if we could find f1 minus 1 for all the instructions, but in some cases it's impossible. For example, on x86, it's an usual optimization to have an XOR like this for setting the register value to 0. So by going backward, we don't know what was the previous value of EAX register, so we cannot find f1 minus 1 function, and concrete reverse execution just invalidates the value for EAX. Okay, for that purpose, we implemented register equivalence analysis. It's a forward direction analysis that is being run before backward taint analysis. It tries to remember for each instruction, for each program point, actually a table of equivalent registers. So let me get back to the same example. By going backward from XOR instruction, as I've said, we cannot taint concrete memory addresses if it depends on EAX by using concrete reverse execution, because there is no f1 minus 1. But by having a register equivalence table, we would potentially have another register for which we know that the EAX is equal to, so we would be using that value instead, which is EDX for this example, and we would be able to calculate, actually to taint concrete memory address if it depends on EAX. So this is an example of how such a table looks like for those two instructions. Next slide, please. As an outcome of the whole analysis described in the previous slides, we have a graph that represents the flow of this tainted critical data going backward from the crashing point. A node in such a graph is represented as a triple of frame level of the function comes from, machine AI instruction, and tainted operand from that instruction. In addition, we have these two types of edges: assignment edge, which is being created only if the critical tainted value was transferred from one location to another, and ref edge, which is being created if we detected loading, actually setting of that critical value. Finding the blame function algorithm. First of all, I just want to mention that there is an option for printing the graph in form of dots, so we can use a graph quiz to visualize the graph. We implemented that. On the picture on the right, we can see an example of such a graph. assignment edges are black, deref edges are red. So I don't want to spend too much time here because Nikola will show some real examples during the demo. But in general, how algorithm for finding the blame function works, it's a classical DFS algorithm on a very high level. By tracking only the assignment edges, it tries to find the node at deepest level, which contains the deref edge, which means that it is the first program point that actually sets that Baev critical value. So yeah, we have open sourced our work. This is the link of the project. Please feel free to clone the repo, and any contribution is welcome. I want to be clear that this is still in work in progress stage, but all the key building blocks are implemented. But all that needs improvement in order to cover more and more real cases. For example, concrete reverse execution handles some of the x86 instructions, but not all of them. So the more instructions we add there, the more concrete memory addresses we have, and the more cases we cover. But all in all, this is very good starting point. We often face some real cases where it works, but there are a lot of cases out there that we still need to cover. So yeah, this is an overview of the files implement all the key building blocks, actually, key components. So yeah, that's it. Nikola will do the demo.
Hi, I'm Nikola Tesic, and I'm going to show you how to use LLVM Crash Analyzer tool. But before, I want to show you our LLVM Crash Analyzer public repo. The README here is very informative on how to build a project, use a tool, and please feel free to try it and feel free to ask any questions if needed. Okay, let's start with a basic case, going to the complete process from the buggy source code to the detected root cause of the bug. Let's take a quick look at the source code of the test. At line 6, we have a crash caused by invalid access in the function h. At line 16, the bad value is loaded. So for line 6, we called it crash point, and for line 16, we called it the blame point. Let's try our tool. Firstly, we need to prepare the test, to compile it, to run it. And expectedly, we have a crash with segmentation fault, and Corefile is dumped. So now we can run LLVM Crash Analyzer. We need to use Corefile arguments to specify Corefile. Also, it is mandatory to use executable. If we want to see exact line which caused the crash, we could use print potential crash cause log. If we want to see flow of the tainted value line by line in the form of the data flow graph, we could use print taint value flow as dot. These two arguments are useful for users to track the bad value fully or partially in the source code. If we want to inspect generated machine IR, use print decompile machine IR option. And if we want to see the flow of the tainted value in the machine IR level in the form of the graph, we use print dfgs dot option. Last two arguments are useful for the tool developers to determine where the tool have lost the track of the bad value. And from the tool output, we can see the first phase is reading the core file. The second phase is decompiling functions from the backtrace, and then analysis is performed. At the end, we report blame function and the source code file and line responsible for the crash, which we can confirm in the source code. It's line 16. Yes. Okay, let's take a look in the tool's outputs. Okay. Firstly, notice in the machine IR generated by Decompiler, IR module containing IR functions, which are dummy, having no code, but having attached debug info subprogram, which is needed for correct blame function report. After section the debug info metadata, we see decompiled machine functions. Please notice newly added attribute reginfo containing register values at the time of the crash, and also crash order number. Among the machine instructions, please notice crash start flag, labeling the program port from which we start our backwards analysis. Okay, let's show the graph. On the right, you can see the graph showing the taint value flow in the machine IR level. Each node represents a tainted value at the program point containing crash order, machine IR instruction, and a tainted location, register or concrete memory address. Red edges represent dereferences and black ones represent assignments. In the machine IR, we start backwards analysis from the crash start machine instruction, the first frame, and track locations which contain the bad value in the backwards direction. And we populate the taint data flow graph. Firstly, the location is RIX, then memory address at RBP-8, and so on. We are following the principle of the concrete reverse execution. When we reach the parent frame, we start from the instruction above the call, although crash start marks instruction after the call. In the function f, as seen from the graph, crash order 3, we encounter instruction which loaded constant 0 into the taint location. And there we stop the analysis. By finding the deepest dereference in the graph, we determine the blame instruction and therefore the blame function. Okay, let's quickly switch to the second case for which we have previously prepared outputs to save some time. Please notice in the outputs that func1 is reported as a blame function, but it is not decompiled since it is inlined into main. But we are able to report it as a blame function because we are using available debug information. Let's quickly check generated machine IR. Please notice that inline function, func1, does not contain any machine instructions. They are in the main frame. Let's check corresponding graph. From the graph, deepest dereference is loading some big constant. That is the end of our backwards analysis. And we found that instruction in the machine IR. By inspecting attached debug location, we see reported is line 27, and we found the scope 5, which is different from scope 7. Why? Because the scope 5 is from func1, which is inline, and scope 7 is the original main function. Okay, let's quickly inspect our case of the artificial bug from the LLVM project and previously prepared analysis output. From the output, the beginning, we are seeing the compilation of the functions from the backtrace, around 10 of them. But during the analysis, we see the compilation of many more functions decompiled on demand. That is the most time-consuming part in the analysis of the big projects. At the end, blame function is reported and line number 4183 in the x86 instruction info. And we can compare it with the source code, and it is definitely the point where we inserted our artificial. Thank you for your attention during the demo part, and now I'll let Djordje conclude this presentation.
Thank you. Thank you, Nikola. Let me quickly wrap this here. We developed this LLVM crash analyzer, LLVM-based tool used for program analysis. It tries to identify function that is responsible for the crash, which should help in reducing the time for root cause analysis, and it can help Q&A engineers when filling bugs. Current support is there for x86-64 only, but there is nothing target specific in the design of our tool, and it could be ported to other architecture as well very easily. Definitely there is work to be done in order to achieve production quality. So again, collaboration is allowed. Thanks again for your attention, and please feel free to ask any questions. Thank you.
Okay. Are there questions? Anyone? I have a question. First of all, I'm super excited to see this presentation. I work on mobile performance and reliability, and we this, like, I guess people are missing a tool like this, basically. The crash reporting systems that we basically pull from open source, or you see tools available there. Your tool is like much mature because it gives like really what ideally I would like to have. The question I have is, you're using the core dump file, and often the core dump files are large. Have you looked into like decompiling by using the mini dump files? Essentially, we had to have less information, but have you given a thought about it?
Actually, for this initial stage, we haven't, but yeah, we are planning to do that as well. But for the parsing of core files, we are using LLDB library, and algorithm for that is pretty fast. But yeah, core files could be too large. So yeah, thank you for that question.
Yeah. So David asked that any plans to upstream this tool in future?
I mean, we open sourced that, so you can find
it says that it is
here.
Based on LLVM 10.
Yes, and we are planning to spend some time to rebase this work on the latest LLVM. But yeah, I mean, why not? One day it could be a sub-project of official LLVM project. I mean,
yeah.
So.
Awesome. One reason I'm very excited is, like, almost 2 years ago, I was trying to do something like this, and I had a couple of ideas, and you might find it interesting. Like, once you have the, let's say you decompile and you have the like stack trace, which is now symbolicated, essentially, like you have the call graph, so to speak, right? Now, it is possible that some of the entries in the call graph are not fully known. You know, let's say you have indirect function pointer or something. So the back, you might have potentially multiple edges, right, instead of one. And it'll be interesting to you can use actually like some graph algorithms to minimize the set of potential edges. Okay. Basically, like if you have function pointer, then it can point to so many functions. But if you use the source code based, like original source code call graph and compare to the crash log call graph, it will help minimize the set, and that way the developers or people who are looking at the crash log may easily like reduce it. Their consideration set will reduce dramatically.
Yeah, yeah, but yeah, I also want to mention that at the moment we don't handle indirect calls actually.
Okay.
So
Yeah, it's not possible to handle that one. But
yeah.
you might, like, let's say indirect function calls are like holes in your call graph. But before and after, right? So, and those edges can be reconstructed based on the source code call graph and crash log using like depth first search or something like that. You can like, there are certain ways to do that. I can talk about it more later, right? Maybe.
Sure.
Yeah. Okay. Got any more questions? One more thing is, when you do the decompilation, like there are certain like the compiler itself has some like non-determinism, especially Clang. Like if you compile the same source code again and again, there might be certain variabilities, like let's say registry allocation, or Clang uses hash map or things like that, which can, there will be slight difference in the binary. Have you encountered such problem in your experience, or no?
Actually, no, we haven't faced any situation where it could actually make some, I don't know, situations for our needs. So because we mostly, whatever the assembly is and whatever the compiler was for producing the final code, let's say ELF, on Linux, we just analyze that final code. So whatever heuristic was during the register allocation or something like that.
So far, we have found a almost one-on-one mapping to the MIR and the assembly.
Okay, that's pretty interesting. That's cool. Okay, good to know. Awesome. If there are no more questions, then yeah, thank you again for presenting. It was quite useful.
Thank you.